All right, next topic is what's called an LSRL. We're going to talk about what it entails. So let me get this started. All right, so let's start with just some general understanding about bivariate data. We've got X, which is considered to be the independent or explanatory variable. Y is the dependent or response variable. When we're looking at LSRLs, we're looking at predictability. So how well does X predict Y? Y responds to what X does. X explains what what Y does. That sort of thing. We typically use this equation of Y hat equals a plus bx. Y hat is an actual symbol, and it represents the predicted y, the predicted value of it. And you do need to make sure the hat is there. B we refer to as the slope. And one of the things in statistics we want to get sort of used to understanding is a lot of times they'll ask us to interpret things. Describe what this means. Tell me, and a lot of times it sounds like someone's trying to get to know you and they want you to express your feelings on something. And honestly, in statistics, that is not the case. We have a set phrase we want to know that you know. So when you're asked to interpret slope, the phrase is, it is the approximate amount by which y increases when x increases by 1 unit. Now, we're going to add some better words than y and x and units, but that's what slope means, is that when x gets bigger by 1, what is y doing? And then a, of course, is the y-intercept, just like Algebra 1 in high school. Same old, same old. It's the approximate height of the line when x is 0. And a lot of times, the y-intercept really won't make a big difference other than a starting amount. The interpretation piece usually gets done when we talk about slope. Okay, so LSRL formally stands for the phrase least squares regression line. So let's kind of talk a little about what we mean by least squares regression line. This is the line that gives the best fit to the data set. In other words, it's the one that does the best job predicting y from x. And we'll kind of talk about what it means when we say this phrase minimizes, but it's the line that minimizes the sum of the squares of the deviations from the line. So, and again, we'll kind of get to visual on that. Okay, so let's take 3 points, and I'm gonna just make up a line, not the line. I'm just gonna make up a line that I'm gonna claim can be used to predict those 3 points. Now notice none of the points are on the line, and that's okay. So there is an amount of error that each of the points produces. So if I take the predicted value, so for that first point I predicted 4, it actually was 0, so that meant I was off by -4. We go to the second point, 310. I predicted using this 0.5x plus 4, I predicted 5.5. That meant the amount I was off was 4.5. And same with 6 comma 2. So I'm going to use the equation, predict what I think it is at 6. I think it's 7, and it actually is 2. So I'm off by 5. Now, if you remember when we looked at standard deviation, we didn't just add up the error and use that. We squared it, made everything positive, and then we sort of found this average error number. Well, that's the same idea with this sum of the deviations from the predicted value. So when I square each of these numbers, when I square the -4 and square 4.5 and square -5, the sum of these squares is 61.25. Okay. Now let's take that in perspective with a calculator. Now let's let the calculator do the line of best fit. So we type the 3 points in, and we do that's that linear regression screen that I was showing you with R. And the calculator actually gives us this line, the 1/3 x plus 3. And now notice none of the points are on the line. Okay, so there's an error for each point. And so we're going to find that. So if I take the first point, I get an error of 3, so it's a -3 off. The second point is 6, and the third point is off -3. Now, when I square these numbers and add them, I get 54. Okay, so in other words, I had two lines. The first line, I had a higher sum of the squares than 54. And so what we claim the Lsrl does, the least squares regression line, is it minimizes this deviation, minimizes how the error for each of the sets of points. And the calculator does a lot of that calculation underneath the hood for us, but just got to appreciate that when asked, what does the Lsrl do? Why is that the best line? That's because it's the line that minimizes the deviation from the regression, from the line. Okay, so back to what I was saying earlier. A lot of times in stats, they're going to ask you, what do you interpret this to mean? What do you think this means? And it's going to sound like they're asking you feelings questions. They're not. No one cares what you think. We want to know what is the phrase associated with, in this case, slope. So for each unit increase in x, there's an approximate increase or decrease of b and y. When I walk around and look at everyone's homework paper or test papers, it should look like everyone's copying the same sentence, because you're writing down this phrase. Now you're going to fill in the blue stuff with actual verbiage from the problem. Correlation coefficient, same thing. There is a direction strength linear association between x and y. Those words can change depending upon the type of analysis we come up with. Okay, so let me pause this here. Let's take out our calculator and let's type this in, and let's come up with our R and our least squares regression line, and let's figure out what slope is. Let me pause this so we can do that. Okay, so now that I've got the data typed in, I'm going to go calculate the line, and I'm going to store it this time. So x is list 1, y is list 2, and I want to store the equation. So if you remember, we go to vars, go to yvars, and then tell it I want you to remember this under y1. Okay, and so we want the slope and the correlation coefficient, because we're going to write a sentence about that in a second. Now, just to show you what that whole saving thing did, if I go to y1, it actually stored the equation there, and the benefit is I don't have to write all those decimals down. So that was a nice little benefit for us. Okay, let me go back to the home screen. In the event that you don't have the data on your screen anymore. Okay, so using these numbers, we're going to interpret slope and the correlation coefficient in context of the problem. So x and y, meaning x means ages and y means heights of the children. Okay, so our correlation coefficient would be phrased as there is a strong positive linear association between age and height of children. So notice I filled in the blank based on what R told us. R was a fairly strong R, and it was positive. Now that word linear, we still haven't talked about how to tell that yet, but we're getting there. And then the x and y, instead of saying x and y, we put in the actual phrases that mean x and y. Our slope would be, for an increase in age of 1 month, there is an approximate increase of 0.34 inches of heights of children. So the 0.34 was the slope of the line. It was positive, which meant it was an increase. And then we just filled in context of what the other information meant. So X meant months and Y meant heights. All right, so now we're going to use our calculator again and predict, because we have this nice lovely equation, um, the heights at those two ages. Okay, so the nice thing about typing in or having the calculator store that equation is I can actually take advantage of it. So if I go to vars and then go, I just want y1, so go to function and then y1, parentheses, because this is a function now, I can just type in 4.5 and it will predict that for me. So at 4.5 months, I would expect the child to be 21.94 inches. And then I can do the same thing for the 20. So go to Y1 and then just hit 20 and it will do the same prediction. Okay, now, so that's a nice little feature the calculator has built in. We do want to be careful with something called extrapolation. If we can do it. Just because we can predict doesn't mean we should predict. If we predict outside the range of our Lsrl, so let me kind of go back. What am I talking about here? Oh, I'm sorry. Wow, I completely misread this question. 20 years old. Go back to the calculator. I'm wrong. I did 20 months. We want 20 years. All right, so this is quick fix. All right, so 20 years. So that'd be 20 times, there's 12 months in a year. Okay, so we get this height of 102 inches, and you're like, how tall is that? Well, there's 12 inches in a foot. So according to our equation, the height would be 8 feet 5 inches, which is ridiculous that that would happen. Anyway, so going back to what that tells us, just because we can use the equation to predict doesn't mean we should. And so that idea of that I can predict it, but the interpretation of that number might not have any real world connection, that's called extrapolation. We shouldn't be predicting outside that range. Now, I might be asked to, but it's kind of like a warning. You might ask me to predict this. I'm just going to tell you ahead of time that my prediction might not have value or meaning for us.